Hi guys, welcome back to my YouTube channel. Um, Today we'll be dealing with hydrodynamics, which is it's another topic which will focusing on the flow in pipes. Right, is hydrodynamics. This is N5 fluid mechanics. It's N5, right? So um, you must know when you're given hydrodynamics, you must know something which you call Reynolds. We have Reynolds, right? Reynolds number. Reynolds number. We have what we call Reynolds number, right? So Reynolds number, it's Reynolds. You'll write like this, and you put in. This is given by coefficient of viscosity. We multiply by the diameter, divide by velocity, right? This is a Reynolds number. It's how you calculate it. It has no SI units. So this is a Reynolds number. We're talking about a Reynolds number. So since you have this, I want you to check. We have two formulas. This you can say it's a formula 1 for Reynolds number. I want us to check if you have given kinetic viscosity. We've learned about this. We know kinetic viscosity is coefficient of viscosity or dynamic viscosity divided by what? By density, or it's rho. It's one and the same thing, density and rho. Divide this by a density. I want us to check now. We divide this by the density. This is what it is, right? We have this, which is Reynolds. Well, this is a coefficient of, this is a kinetic viscosity, right? There we have Reynolds, right? Right. So there we have that. So we're supposed to use our thing here. This is not the velocity. Sorry. This is like this, right? It's coefficient of viscosity divided by diameter divided by kinetic viscosity. So it's coefficient mu. This represent coefficient of viscosity. This is the diameter of the certain pipe. This is a kinematic, right, viscosity. So we have this is formula 1. Now we should have formula 2 for Reynolds. We derive it. We have this kinematics viscosity. Also this is kinematics. So we can make this the subject. So we know this, okay, already it is in the subject. We can take this and substitute there. If substitute there, we'll have Reynolds is equal to coefficient multiplied by diameter. We'll substitute this. Remember this and this is one and the same thing. Will be mu multiplied by what? By density, right? You have this now. If you do your maths there, you know you will multiply the bottom and the top, or multiply this by density over coefficient. The bottom and the top, also here multiply by density over coefficient. This and this will cancel, this and this will cancel. There will be have this will multiply, there will have coefficient multiplied by density diameter, right, over that will go there. Yeah, right. and that will go on the top. Then this and this will multiply. We'll have this over that. Right. That is it. We'll have that over that. We'll have that over that. This is the formula 2. We have derived the formula 2. So we have formula 2 for Reynolds, right? So we have given the example here. We'll come to that. We have derived this. This is the formulas you must know. Let me just say, remember, let me just say like this. This is the formula we must know. Right, is formula 2. So what do we know again? If Reynolds number is greater than, is less than, let me start, is less than by 2100, right? If this is less than 2100, right, this will call this a laminar flow. Laminar flow. Then if Reynolds number is greater than 2400, if this Reynolds is greater than 2400, this will call this turbulent, will be a turbulent flow. Call this a turbulent flow, right? This is a Reynolds. So we're given an example here. It says a fluid with a relative density, of 0, right? This is a relative density, right? Is the same as specific gravity, which they've given us is 0,8, right? So we know that relative density or specific gravity, it's one and the same thing. Relative density is equal to what? The density of the substance over the density of water. Whereby we know this Reynolds we're given here. Substitute the Reynolds number here. We're given, which is 0,8 over multiplied as by the P of the substance that we're looking for. We divide this by 1000. That's the density of water. You multiply that side, you'll get that density. When you multiply that, will be what? 0,8 multiplied by 1000, get 800 kgs per cubic. That is what is the density here, right? That is a density, right? So we have this density, right? For that, so we have this. We have given the diameter of the pipe to be 25 millimeter. Divide by 1000. We'll get this to be 0,025 meter, right? You can punch your calculator, divide by 1000, right? This will be in meter. You have given a velocity, which is 2 meters per second, right? At the velocity, this flow is flowed at 2 meters per second. The coefficient of viscosity of fluid is this. Pass the coefficient, we know, coefficient of viscosity, they've given us there is 0,01 pass, right? We have this. So they said determine the type of flow. For us to determine the type of flow, we must find out the Reynolds number, right? We must find out what is the Reynolds number, right? So that will be fine with our stuff there. If you can find the Reynolds number, then we will be fine, isn't it? Right. So know that the Reynolds number will be density. Let me say this is U, is velocity, right? Multiply by diameter over coefficient of viscosity. That means we've proven that from this stuff, right? You remember, we've proven that what this will become. So we have this, right? So let's substitute density. It's 800 multiplied by this. Actually, this is a velocity. This U in N5, U is similar to velocity, but mu K is viscosity. Viscosity of the what is the coefficient of viscosity. So this is U, it's a velocity, right? Then okay, multiply by the velocity, which is 2, multiply by the diameter, which is 0.025, divide this by 0.01, divide this by the coefficient of viscosity. Then you come, you punch, you calculate 800 multiply by 2 multiply by 0.025, right? Divide this by 0.0, divide this by 0.01, right? We'll get this to be 4,000. So 4,000, therefore 4,000 is greater than what? 2,000. Yeah, 2 is greater than 2,400, right? So this is a Reynolds number, right? So 4,000 is greater than this, then can completely say this is a what? Remember, it's a turbulent flow. Why? Our Reynolds number okay, is greater than 2,400. This will be a turbulent flow, right? So yeah, this is we're dealing there with Reynolds, right? We're still under Reynolds, right? So I want us to check. Let's say now I want you to check velocity flow. We have a velocity flow, right? It's a velocity flow which will have a dot here, will represent by a dot, which this is equal to volume divided by time. Remember, this is a velocity flow. This will be a velocity flow, right? Okay, let me not say velocity flow, sorry about that. What I'm trying to say, it's a volume flow. It's a volume flow. This will be a volume flow. Which is volume flow is the same as the rate of flow. Remember, the rate of flow is calculated by area multiplied by velocity. So that means this V flow also can be calculated by what? By area multiplied by the velocity. So this will be two equations for volume flow, right? For rate of flow or the volume flow, right? So it's given there is a dot, it's V with a dot here on the top, right? I hope you understand. This V with a dot here on the top. So I want us to check. I want you to, okay, mind you, we have also what we call mass. This will be a mass flow. Remember, mass flow. This can be equal, there's M, it's a mass, it's M with a dot here on the top. You put a dot to show this is a mass flow, right? Isn't it? Remember, mass is measured in what? In kg, right? So mass flow, when we have a mass flow, that means there must be time that is included, so to flow in the certain. So this is a mass flow, right? So I want us to check here, how can we find the mass? Mass will be given by what? If you understand, it's either way. Mass, remember this is measured in kg. How can you derive kg? How can we get kgs, right? So so let's say now I have the density here. Density is measured in kg, right? We have kgs per cubic, which is fine, you see. But now mass is calculated, but the mass must be calculated in kgs, right? But the mass flow is calculated in kgs per second. How can we derive this? How can we, what equation, what can we make so that we have these SI units, so you understand? So what we will need there, we must know that what we will need there to have this mass flow like this, right? So let's say now, imagine, what can I use? What can I multiply? I must multiply with something to cancel this. So I'll multiply this by what? I should multiply this by the flowing velocity y. Look, so that we know this, the density is measured in kgs per cubic, right? Right, or let me write this per cubic centimeter. This is the same as like a fraction. It's the same as kgs divided by cubic. This is one and the same thing, right? Multiply this by this. This is measured in what? Is measured in cubic meters, but what? Per seconds. But this is the same as over, right? So you see, this and this will cancel, we're left with kgs per second. So this is what we wanted to have, right? This is what we wanted to have. So that means we can conclude, therefore, can conclude that the flowing mass will be given by the formula, will be density multiplied by V, the flowing volume, like this. This will be our mass flow. So I hope you understood this. But now, since we have a mass flow, we can also have the force flow. For example, okay, let me just say weight flow for argument's sake. W, we know this is measured in what? In Newton. It's measured in Newton. What is Newton? Remember, Newton must be, and here this is mg, right? Newton, to have a Newton, we must have kgs multiplied by meters per second squared. For us to have a weight or a force is equal to what? Is the mass of the object multiplied by the acceleration. So, or this is an SI unit for what? For a Newton. When you see this is the same as what? This will be same as what? This Newton. That will be what? Newton, right? You understand? Now, but now, in this topic we'll conclude, we'll have dot here. So we must have mass flow. That means you must have W with a dot must be newtons per second. So to have that, so we have this, which is the mass. Yeah, it is good, right? We understand that this is the mass. Yeah, this is good. That is the mass. But now we want to have seconds. What can we do for what can we do here so that we'll have newtons? this will give us newtons, but we want to have this is measured in newtons per second. What can we do to obtain newtons per second? We have let's say now we have this. What can we do so that we can obtain newtons per radians there? What can we do? So it's clearly we want this to be in seconds. So if we want W, the weight flow, we can just make M to have dots. We can multiply with the mass flow and multiply by gravity. Why do we choose in this formula? Why do we use this formula? Is because if you check, why do we use this formula? Because the mass flow will have the seconds, will have this is measured is kg per seconds, right? And then that this gravity is what is in meters per second squared, right? So this is the same as kgs. If we write this per seconds multiplied by meter per second squared, this is the same as this, right? We have this now. So we have tried and manipulated stuffs and stuff. We've tried. So we saw. Let us erase here. Now, so we know as a newton is kg multiplied by meters per second squared, right? This is the newton. So how can we make this as a unit? We know if we take this, if we group this together and we exclude that as, we'll have this kg, right, multiplied by cubic meters per second squared. But we left with s. It's s here. You see, we do not include this s, which is per second. We have these seconds. But what about this? We know this is the same as this is newton, right? So we can substitute this newton here. Then this will be newton. But now we have the seconds that is left over per second. So the weight, the flow must measure in newtons per second. So because it's a weight flow, since we have the weight flow, that means the weight flow, its formula must equal to mass flow. So that multiplied by gravity. You understood this. Hopefully you understand this. Must be like this. So we'll have this in newtons per second. So that we'll end up with this. Now we understand our stuffs. So since we understand these stuffs, we can deal with that example. So simple, right? So we are given an example there. We are given an example. We're given an example, isn't it? Says example 1, determine the feed in. Well, we will see. They said we should determine the volume flow, the mass flow, and the weight flow. We want this 1, 2, 3. This is what we're supposed to calculate. This is what we want, that stuff's there, right? So since you want this, let's read of fresh water. This is a fresh water supplied. If they give you water, this is a fresh water. The moment when you are dealing with fluid mechanics, you hear the word water. What is coming in your mind? Water. Under fluid mechanics. When you hear this under fluid mechanics, if you're a fluid mechanical, under fluid mechanics, you must know they talk about the density, which is the density is 1000 cubic kg per cubic. Right, this is density. They won't tell you the density of water is 1000. You must know this by heart. So when you see there's a flow and in that flow it's water, just know the density is 1000 there. They try to tell you, bruh, since you know, anyway, you're an engineer, you know what is fluid, right? So you know what is the density of water. Density of water is 1000. We cannot tell you this because the standard, it does not change anyways. So they want you to discover this, to know this anyway. So we have the fresh water. We know this is a water supply which fills a tank with a diameter of this is of, we have the diameter there of 2 meter and the height, right? By given the height, its height here is 2 meter, right? The height of that is 2 meter in seconds. 2 meter in seconds, right? Is this in 2 hours? Or is in 2 hours, right? We have that. Hopefully you see that these two, right? Is that we have that there. So there we've given that is a, you can hear, right? It's a height. Height obvious is h is 2 meters. So let us calculate the volume. Let us start with this one. We know that, let me just say solutions. This volume flow, we know this will be volume divided by time, right? So we don't know the volume, right? But time, we're given the time. So we can calculate the volume. The volume is what? You must know the volume, that it's area multiplied by what? It's either, if you're dealing with a piston, will be a stroke length, but if you're dealing with a pipe, or you're dealing with a pipe which is faced vertical, or however, will be h, the distance that the water traveled, right? This is just h, which is the height, will be h. Why? Because area is measured in cubic, and then h is measured in what? In meter. When we multiply these two, you will have cubic meter, and then volume is measured in what? In cubic meter. That is why we multiply by this height. So we know this is a what? It's a pipe. We have a diameter. If we have a diameter, that means it's a cross-section pipe, right? It's a circle cross-section pipe. Cross-section of this, it's a circle. It's a circle. Now we know this will have pi over 4 multiplied by d squared multiplied by h. This is, remember, this is what? It's the area multiplied by that. So let me calculate right here. This is what will be measured in cubic meter, right? Which is, this is a volume. Now we can substitute our values here, right? So that we'll have that. Now we know this is pi over 4. The diameter here is 2. We square that, multiply by, also that is 2. Okay, right. Let's have our volume. What will be our volume? Let me punch my calculator so that I will have the volume there. What will be my volume? Pi over 2. Let me clean this calculator first. Right. Pi over 4, 0, 2 squared multiplied by 2. This 4 over pi over 4 into 2, you square that, multiply by 2. The volume is supposed to have 6, 2, 8, 3. This is in cubic meter, right? That must be in cubic meter, it's just the volume. But now we have the volume, can substitute this volume here. We have time, right? So our V will be volume over that. We have volume here, its volume is 6,283 divided by time. But the time must be in seconds, so you must know your stuff. 1 minute is equal to what? 260 seconds. 1 hour is equal to what? 260 minutes. You see this? Do you see what is happening here? We have that. But for you have 2 hours. You have 2 hours. But now since you have 2 hours, right, you want that to be in seconds. You see? So what about minutes? Let's focus here. Let me square this. Use the proportion. If you have 4K10, you can use the proportion. 1 hour is equal to 60 minutes. But as they've given us 2 hours, we don't know the minutes. You can say X, you cross multiply. There you have X. Then you multiply that, will be 2. Multiply by 6, you cross multiply. You'll have this. Remember X, this was minutes, this represents minutes, that this will be in minutes. You'll have this. Now, you come again, we are done with this, but you want it to be in seconds. You go to this proportion, right? But you know that 1 minute is equal to 60 seconds, right? So, we have minutes here, this represents minutes, right? Is 2 multiplied by 6, right? This is in minutes. What about the seconds? You don't know the seconds. You cross multiply again. You multiply there, multiply that, X, 1, this 1 multiplied by that will be X, right? You multiply that. Oh, sorry, multiply this, there is 0 here. Is 2 times 60, right? Minutes. This is 62 multiplied by that will be 60. Also here will be 2 multiplied by 60. We know this. You deal with the proportion, you multiply there, you multiply there. You will have 2 multiplied by 60. This multiplied by that 60. But this X is in seconds, right? That means this will be the time. Will be in seconds. Right, that means when you from hours to, if you want to convert from hours to seconds, you multiply by 60 twice. If you have 4 hours and you want to go to seconds, you multiply this by 62 times, right? Then this will be in seconds. The answer that you will get, you must know the conversion. You must know how to convert. You must know how to convert. Use the proportion. It's important to understand that we have 2. We saw this would be 60 multiplied by 60, right? 6,283, 2 times 60 times 60, right? the flow will be 872,639. Right, this we multiply this by 10 to the minus 6. This will be in cubic meters per seconds. Right, that is our answer. Right, I hope you understood this, guys. So this, we have this. Now let's find the flow in mass. We know that the flow in mass will be what? We want the flow in mass will be a density multiplied by the flow, right? The density to water, remember this will be 1000 multiplied by the V flow, which is what we have here, which is 872,639 times 10 to the power of negative 6. Punch that on your calculator, M flow. Punch this on your calculator, right? So if I punch mine, just 8,000 multiplied by 872,639 times 10 to the negative 6. You see, I got 0.87. Run this to 3 decimal, will be 3. Right. Remember, this will be what? Kgs per what? Per seconds. Remember, this is a mass flow. If you see that dot, you see that dot there on the top. That dot tells us this is a mass flow. So we have this. Now let's weight. We've done. Now we want the weight flow. We know that weight is given by mass multiplied by gravity, but now it's a weight flow. Then we will use the mass flow. We must have what? Mass flow there, right? Multiplied by gravity. Must have a mass flow. The mass flow is this. We've calculated 0.873 multiplied by 9,81. W. Mass flow, what is the mass flow there? 0.873, right? Multiplied by 9,81. This is what? It's 8,564. Round this to 3 decimal place, right? So you know most. This is kg, but now it's a weight flow, right? Will be, oh, it's a weight. Oh, sorry, it's a weight. Weight is measured in Newton, but now it's a weight flow. Will be newtons per second. This is what it is. This is what we know. Hopefully you understand this, guys. Right, that it is. Let us try another some question. That is what we have there. Right. Also here we're given this question says determine V with a dot here on the top. What is that V on the dot in the flop? And M with a dot on the flop and W with a dot on the top. We know that it's a flows. All of those things are flows. Volume flow, mass flow, weight flow, right? Simply what they mean. And then now here, guys, we have these flows. These are flows, right? Of what? We have water. He said when we have water, we know that we are talking about the density, 1000 density here. But if you are not given a water, if they did not mention water, and then you are not sure what is flowing, they're supposed to give you maybe a specific gravity. They will give you a specific gravity or something so that you will calculate the density. But if they tell you that it's water, it's unnecessary for them to tell you, oh, you know, but the density, take it as 1,000. No, unless they give you otherwise, they state otherwise. But you must know that the water will be 1,000, its density. So the water jet, they've given us, this is a jet there with the with jet, when this is a jet, that means diameter. The jet is 25, jet 25 in diameter. This is the diameter. It's 25 divided by 1,000. This will be 0.025 meter. Right. Meter, and having a velocity of, you have given a velocity. This is a velocity which is 3 meters per second. Right, we have this. We want this, that, and that. And the kinematic and calculate again here the kinetic energy. Right, you know the kinetic energy, isn't it? I hope you know the kinetic energy. Briefly, you must remember that you can see Ke kinetic energy is 1/2 Newton mass velocity squared. But now, if we're dealing under hydro, we remember this is hydrodynamic, it's a flow in pipe, right? So since it's the flow in pipe, we're dealing with flow in pipes. Flow in pipes. So since this is a flow in pipes, this must be 1/, must have m with a dot here, must be mass flow. This must be mass flow. Must be a mass flow. Must be a mass flow, because we're dealing with a flow. Obvious, it's a flow in pipe, so must be a mass flow. So let us start with that. They want V, this. We know that, or we use what we have. We know V is what is V/T. We don't have time. This formula will not work. We also have this is equal to area multiplied by velocity. We have velocity. We have the time to calculate area. You check, since you're not given time, this formula will not work. Where is my wipe? I don't say, okay, no problem. I want something to wipe here. Cannot use hands. Right. So now this will be area multiplied by the velocity. Area is pi/4 d squared multiplied by v, pi/4. Diameter is 0.025. You square that, you multiply by the velocity, which is 3. Then this pi/4 into 0.025 squared, multiply that by the velocity, which is 3. You will have this 1.47, round this to 3 decimal place, will be 3 times 10 to the minus 3. This measured in cubic per second. So remember, this is a flow, cubic meters per second. This is that is the flow, right? So we're done with this one. Let's go to the second one, the mass flow. We know the mass flow. Either way, we know that the mass flow must be equal to density multiplied by, right? Density multiplied by V flow rate. So density is water. Either way, we have 1,000 multiplied by this value, 1.473 times 10 to the minus 3. What is this? 1000 multiplied by 1,473 times 10 minus 3. We have this as 1,473. This measured in kg per second. We are done with that. Now we go to the weight flow. We are done with that. Let's go to the weight flow. You know the weight flow. Weight flow is equal to what? It's mass, but flowing mass multiplied by gravity. The flowing mass is this. It's 1,473 multiplied by 9,81. That multiplied by 9,81, 14,45 is 0, 4,5. This will be newtons per second. Right, we have this now. One they can, you know that calculate the kinetic energy will be 1/2, but it will be mass flow under the flowing pipe side. Velocity v squared 1/2. Mass flow is that 1,473. Velocity, which is 3, you square that, multiply this 1/2 into 1,473, multiply that 3, square that. This will be 6,629. Remember, it's measured in joules, but now remember, under the flow, this is a hydrodynamics. Since it's a hydrodynamic, this means the flow in pipe 10 per second. Remember, this is in seconds. This is in seconds. So already this will be joules per second. But this mass is not a mass flow. This will be in joules. That is the difference. This will be joules per second. That one won't be in joules per second. It's measured in joules. Right. Fully understood this, guys? Right. Well, let's check the conservation of mass. Right. So the conservation of mass. Right. The conservation of mass, let's say we're given this is a pipe. This is a pipe tapped. You can say pipe tapped because it reduced the size. Alright, this pipe reduced the size. If you're given a pipe like this, what you must know from this point here, you see I'm showing the hidden dotted until here, there, you take them by 2 by 2 there. Throughout the V flow is the same, volumetric flow is the same, right? Is the same, but let's say this point, the V flow, let's say for an example, if at this point, right, I'm showing the dots, let's say at this point here, the volumetric flow, let's say, is 2 meters per second. Also at this point here will be, the volumetric flow will be 2 meters per second. Also at this point right here of the pipe, the volumetric difference will be 2 meters per second throughout. That means what I'm trying to say, the volumetric flow is the same throughout, regardless the pipe, the shape of the pipe. Even if the pipe is become large or suddenly construct or enlarge, in the flow, in the continuous flow like this, the volumetric flow is the same. And also know that the rate of flow is the same throughout any dots, right? So hope that you understood this. So since it's the same, now we have this pipe here. We are given maybe at this end of this pipe and also this end. We know that the volumetric flow will be the same. Let's say, let me call this part, you see they call it D1, area 1, V1. I can say V1 must equal to the volumetric flow 2, right? Here I can say this is 2, throughout is the same. And then we know this is given by what? V flow, we know this is area. We can use, will be area 1 multiplied by U. Velocity 1 is equal to area 2 multiplied by the velocity 2. By the velocity, this U is equal to velocity. This topic is the same as velocity, which is measured in meters per second. So you must know that is the conservation of energy. We'll apply the continuity formula. So again, the mass flow here, the mass flow here, and the mass flow here, the mass flow here, the mass flow here, the mass flow here is the same throughout. That means I can say the mass flow and the mass flow 1 must equal to the mass flow at 2. And that means this will be density 1 V1 is equal to what? Density 2 multiply by V2. This, we call it the continuity formula. You must know that this is important for you to understand. It is important for you to understand that. Right, you must understand those things. Right, must understand those things. Right. Or we can just say the mass, if you want, again, can be a mass like this, doesn't matter. Also can be so, but density P1, density 1 and density 2 cannot be the same. This is for, it only applies in incompressible fluids. Here we won't deal with the incompressible fluid. Here we'll deal with compressible fluid. So you must know this. But often will you apply this formula? Most of the time we'll use this, call this continuity formula. Right, we'll apply this continuity formula. Right, so you know this, we call this conservation of energy. That means, in other words, from you see this is diameter 1, this diameter 2, we know that V1 must be equal to V2, which is area 1, V1 is equal to area 2, V2. You see, we'll apply, because as long as there is a pipe there. Right, so hopefully you can see that, right? So let us solve this problem. This is problem 1, problem 2, problem 3, right? So let me erase here. You must understand this conservation of mass. Question says determine, we're given this, it's A, the velocity at point 2. Here is point 2, we have diameter 2 here. That means you want the velocity here at point 2, here at out point 2. What is the velocity at point 2? Right now we know, because we can apply the continuity formula. Is the pipe, where the pipe ends, we can take, we know this point to this point, we take by 2, the velocity, and here can take by 3, it doesn't matter, but in every point, point 1 is equal to point 2, the volumetric flow. Understand? So here we know we have point 1 here and point 2. They want the velocity at point 2. Here we have point 1. We know we can say volumetric flow at 1 must be equal to volumetric flow at 2, isn't it? And the volumetric flow is given by area 1 multiplied by velocity 1 is equal to area 1 area 2 multiplied by velocity 2. They want the velocity at point 2, obvious. Must call over, they want this at point 2. They will want V2 will be at point 2. If you substitute, you make V2 the subject of the formula. If you make V2 the subject of the formula, you will find that V2 is the same as this. Make the V2 the subject of the formula. It's where we have the point 2 there. Consider it where V2. Now substitute what we have. The area of V1, we have given the diameter is 150. 150 divided by 1000. This must be 0.15, right? Meter. So we know the area, it's what will be pi over 4 multiplied by diameter squared, which is 0.15 diameter 1. We square this value multiplied by the velocity V1, which is 2, all this by area, this area. So in other words, you can even say, remember area 1, area is, you can also use this formula as this manner. Area is what is pi over 4 multiplied by this 1 squared, right, is equal to area 2. Wait man, what I'm doing here, I mean that area 1 can be pi over 4d squared, right, multiplied by the velocity. This will be equal pi over 4, right, d2 squared multiplied by the velocity 2. I mean this and this can cancel. We can just have d1 squared multiplied by v, d2 squared multiplied by v. If you use this, it's fine. If you can use this, it's one and the same thing. So one and the same thing. So here we'll have pi over 4 its area. Here will be 70 divided by 1000, which is will be 0.07. You square that. This pi and pi will cancel here. Then we're left with this. Punch that on your calculator. You can punch 0.15 squared multiplied by 2 over 0.07 squared, right? You want this velocity, which is 9.184 meters per second. We have the velocity there. You see, it's what it is there. We have this velocity. What done? So we are done with this problem. We got that V2 is equal to 9.18. Oh, sorry, 184 meters per second. When you round it off, 184. I forgot to round off. We're done with this question. Let's go with here. want us to check this one. This was question 1. Let's check this problem 2. We're given this pipe here, right? This is a horizontal pipe. They said we should find, you see I have there's a question mark here. That means we're supposed to find diameter 2. So this is a pipe. You know, there'll be some flow in water here, the flow or in the fluid, whatever, but we want D2, but we know this will be 0.1 and 0.2. This will be 0.1 from this diameter to this diameter. We know that volumetric flow at 2 will be the volumetric flow equal to volumetric flow at 1. So we'll apply this formula here. Let us check this. Volumetric flow at 2 must be equal to volumetric flow at 1. We know this is area 2 multiplied by velocity. 2 is equal to area 1 multiplied by velocity 1. But we know pi over 4 and pi over 4 will cancel out, right? So this we can say D2 squared. Do not forget the square. It will be wrong. Remember, the pi over 4 will cancel with pi over 4. That side will be V squared. This will be D1 squared multiplied by V1. They want diameter 2. We want D2. Can make D2 the subject of the formula. If we want to make D2 the subject of the formula, we divide by V both sides by V2. This and this will cancel. We have D2 squared, which will be D1 squared multiplied by V1 over V2. You take the square root both sides. This will cancel that. We'll have D2, which will be the square root of D1 squared multiplied by V1 over V2. This will be measured in mid. This is the formula. Okay, we'll substitute the value there. So let me move it here, D2. Let us substitute the value. Square root D1 is 150. Is D1, where's D1? Is 50. 50 divided by 1000. This will be 0.05. 0.05, but you square this square multiplied by V1, which is 10 over V2, which is 2. Let's find D2 here. You see, let's find D2. You can punch on your calculator. You can say square root, apply the bracket. You can have 0.052, right? Multiply by 10, divide this by 2. We have 0, is will be 0.11. Round this to the 2 decimal place, right? When we round this to the 2 decimal place, we'll have 0.0112. Right, this will be 0.112. Then if we want this in millimeters, multiply by 1000. This will just say 0.112 multiplied by 1000 will be 112 millimeter. This is D2. Definitely that is D2, right? So we're done with this question. Now we are left with this. I want to explain that. All right. Okay, let me just explain this. You're given something like this. Yeah. Actually, this is the pipe. Can show you. Let me write like this, draw like this. This is the pipe, the big pipe. Here we have the pipe, and the pipe goes like This is the same as like this, goes like that. When it reaches this point, this pipe moves, this pipe do like this, where these pipes do like this. You see, form a flock, something like a flock here. Oh, these two, we'll call these things flock. We form a flock. Here at this point will form a flock. Right. No, so we're given this is, it's A, right? This is B. No, this is B here. This is C. This is D. That means this is diameter. It's pipe. We can call this pipe 1, pipe 2, pipe here. You see, pipe 2, pipe 3, pipe 4 is like this. It's pipe 1. But this is the diameter. I can just say the diameter because this is the same as like this is a diameter here, remember. Also here, there is a diameter, something like this, of this nature. There is a diameter there. So we have these diameters. So according to that law, you must know, we take the points, 2 points, point from A to point from B. That means the volumetric from point A flow to point B, it's equal. You see, must be equal. For me to flow, this and this must be equal. But here, let's say you pour, we have a tap. Here it's a tap there. Let's say you connect this, there's some pipe here. This pipe is used to channel water. This water from the tank, from the tap. This is the water from the tap here. Right. So you release, you open this tap, there will be water. This water is entering this diameter or this pipe here, will move in this direction. This is the water. This water, check what will happen. When the water reaches point B, see what will happen. Some other water will flow in this direction, will split, you see, and discharge at C. And some other waters will and discharge at D. That means if here I've closed the tap, maybe the water that is flowing here, let's say is 2 liters. Let me just demonstrate this way. Let's say now I pour 2 liters. Imagine 2 liters of water here. When I pour, remember this will be 2 liters throughout. The 2 liters will flow here. 2 liters, 2 liters, 2 liters. But this 2 liters, when it reaches point B, it will split. Some other amount will go this direction. Some other amount of what will go to this direction. Right? But we know for sure this will discharge at C and D. But we know this, if we sum up this word, remember this was already, it was a 2 liter, but will split when it reaches at point B. Let's say here 1 liter is the inside, the splitted. Here we have 1 liter, or let's say here we have 1 liter for argument's sake, and 1 liter went through this side. The sum of these two must give us the original amount. So you understand? So what I'm meaning, from here until here, there will be 2 liters that is flowing here. There's nothing has changed until it reaches point B. Still is 2 liters, but will split again, right, when it goes to that direction. That means from here we can apply this formula, right? But you cannot apply it here. You cannot say VB is equal to VC. It's wrong. Why? It's because this water splitted the amount of water here at B, the amount of water here at B cannot be the same as this one, because the water splitted. The water will split, won't be equal. So this cannot work. Will only work in this portion. Will work only in this portion. The conservation of mass. Oh yeah. Understand, the conservation of mass will only work at that positions. Right. So from here will only work here at A and B. But now what about, but we know if you can take V, the volumetric flow at A, we know for sure must be the sum of these two. I pour the 2 liter will split, but I don't know how much amount will go to this side, how much amount will flow this side, but I'm sure that flow, the sum of the two I know will give me the original amount that I've started with. That would be VC plus VD. All I know is that VA must be equal to VC plus VD. It's all I know. You understand? It's what it is. You see that it's not difficult, isn't it? It's understandable. So we have these two equations. We'll use this is equation 1, is equation 2. This is the two equations that you're supposed to know under this topic, right? So you don't have to worry for these two formulas. Yeah, here this is the. So for an example, for argument's sake, let us find the velocity at B. We have given a diameter here. For argument's sake, we can find the velocity there. The velocity, remember, won't be the same, only the volumetric flow. For argument's sake, let's find from between, let us find the velocity at B. Here, this is the one and the same thing, just I enlarge the velocity of B. But we know we have the diameter at A, which is 450. Here we have the velocity. Here we have what? The diameter, but don't have the velocity. So we can use the flow. We can use the flow there. The volumetric from here to B. We can use the composition of mass, right? We can use the continuity. We can use this formula. We know this will be V. Will be velocity 1 multiplied by area 1 must be equal to V1 multiplied by area, sorry, let me just say dA squared multiplied by V. Velocity at A must equal to the diameter at B squared multiplied by velocity at B. But I want the velocity of B, or make velocity VB the subject. This will be dA squared multiplied by VA. Divide this by D squared. See that? So this is not hard, isn't it? Nothing difficult there. Then you substitute. Nothing it is difficult here. Then you substitute. So you know that one to VP, velocity at B. We have the diameter at A, which is 450 divided by 1000, which is 0.45 square. Do not forget to square. Multiply by the velocity is 1.5 at A. Diameter is 300 divided by 1000. That will be 0.3. Then VP. And the calculator, we will see that if I say 0.45 squared, right? Then I multiply that by 1.5 over 0.3. This give me 1,0125. If you round it off, 1,0125 meters per second velocity at B. You see? So I have the velocity now here at B, V at B. Have the velocity. Remember, this is you. You can. It's up to you whether you use U. Remember, U is also. I said U is the same as velocity. You can just use U if you want. You can use U. You can just say U if you want. But me, I'm used to V. You can just say U. Nothing wrong here. You can say U. But you must know this is a velocity. The way I'm used to V is one and the same thing. They won't penalize you if you wrote as V. It's one and the same thing. So U is a one and the same thing as V either way. So we have this velocity now, UP, which is 1,0125 meters per second. So we have the diameter here and the velocity, but I want us to find the velocity at C. The velocity I want us to find the velocity at C now here. Only two formulas we'll use. Once the questions wants you to find something regarding this portion where the pipe split is, you must use this formula. At the flock, here where the water splits, at this portion, the formula you must use, you must say V. It's either you use VA or V. It's up to you. It is this you use volumetric flow at A must be equal to volumetric flow at C plus volumetric flow at D. Also, you can take it from B and sum up this. This can also be volumetric flow at B must be equal to the volumetric flow at C plus volumetric flow at B at D. This is one and the same thing. This is one and the same thing. Because the volumetric flow here and here are the same, this volumetric flow. So it's up to you, it's one and the same thing. You can apply this formula, what is regarding this, but there we want the velocity here at VC, the velocity here. Right, we can make this the subject, which I'll say VC must be equal to V. You can use this formula on the top, take this and make this the subject, will be V volumetric flow at C, and make it the subject will be volumetric flow at A minus the volumetric flow at D. Right, then remember this is still the volumetric flow. Then, but I know the volumetric flow is given by pi over 4 d at A squared, right? Isn't it? Multiply by velocity at A minus pi over 4 d at D, right? D at D squared multiply by velocity at D. That's what I know. So here, substitute, it's a matter of substituting. And here it's just a matter. There it's a matter of substituting. It's just a matter of substituting. Hopefully you can see. Okay, the camera is adjusted right. Okay, I can see. Diameter at A, we know it's 450 millimeter. We divide by 1000 would be 0.45. You square that, you multiply by its velocity, which is 1.5. You subtract pi over 4 diameter at D 225. Diameter at D is equal to 225 millimeter. Then divide by 1000. This will be 0.225. Square that, multiply by the velocity, there is 3.6. Then VC is equal, punch this on a calculator. Punch that on the calculator. 5 over 4, 0.5 squared multiplied by 1.5. Right. Subtract. Oh, be careful of the maths. Here, what must rule? Just use the brackets. Just use this so that you'll be safe. So that you can be safe. Just do like that so that you can be safe. Do like this so that you'll be safe. You see? Minus bracket pi over 4 into 0.225. We square that times 3.6. Use the bracket for, we'll see, has 0.0954. Right. From third, zero 0.0954 must be 0. For if we argument's sake, we must run this to 3 decimal places. Must be 0.95. Yeah, 3 decimal places, 10 meters per second. So hopefully you understand this, guys. Hopefully you understood this. You understood this. You understood this. Right, the conservation of energy, right? So what you must know again, how conservation of energy. Conservation of energy, let's say now you have now must know potential energy, rate. So potential energy, we know this PE, potential energy, is equal to mg, or everyone know this is equal to mgh, right? So potential energy. But now here in the dynamic, this is in right, but here in this topic, this will be equal to, this is the same as weight, right? Multiplied by what? Which this h can replace it by z. This z will know it is the z. It's a static pressure, which can be static height. Anything will you this z will take it from the Bernoulli's equation. This will be z from the Bernoulli's equation. That is the height above level. This z is the height above level. Must know that. Right, so we have again pressure energy must know again the pressure energy, but also pressure energy is also known as pressure head. You can say this pressure head. Right, this is P over density, which is rho multiplied by gravity. Call this, it's a pressure head. Right, this is pressure head, density divided by, what is this, divide this by what, by density multiplied by gravity. We have, this is pressure head. Right, so we taken this from the Bernoulli's equation. Take that from Bernoulli's equation. That is from Bernoulli's equation. Right, pressure energy. Remember that pressure is pressure energy of fluid. Can, for argument's sake, can be per weight. If you multiply by weight, that side be for argument's sake. But anyway, it is fine. Let us just deal with it there. Pressure energy is in it. So let us deal kinetic energy. I'm sure we've discussed about kinetic energy. I'm just leaving you so that you see here where I have discussed about the kinetic energy. Again, we have kinetic energy, which is 1 over 2 v squared. Right, it's a kinetic energy, Ke. Where is my, I lost it. Where is my erase? Ish. Yeah. Right, so this is a kinetic energy. Okay, this you must know this. If they want potential energy, use this formula. If they want pressure energy or pressure head, use this formula. If they want dynamic head, we have dynamic head, or velocity head. You can just say, or velocity head is V over 2G. So V squared over 2G. So this, we found all of this. Actually, we take this from Bernoulli's equation. Bernoulli's equation is, we'll just have this will be pressure. Maybe you can say pressure 1 over density plus, let's say, V1 squared multiplied by 2G plus Z1 is equal to P2 over PG plus V2 over 2G plus Z2. We call this Bernoulli's equation. From that potential, remember potential, we said P is equal to mg, right, multiplied by H, but now we said this P is weight multiplied by Z. We're talking about this Z. Depend which one will you use. This is that Z, isn't it? So in other words, you must know this here. This is what is the pressure. We call that pressure head. We call this dynamic or velocity head. Dynamic head or velocity head. This is a static head. This is a static head. Then we have H, big H. We have H1. Also we have, you see I write it in capital H, capital head H2. H1 and H2. H1 is the whole of this. In this Bernoulli's equation will be, you take this all, you understand, all of the left hand side. You're supposed to take that all of the left hand side. Take the all of the left hand side. That will be H1. All of the left hand side. Here it's the left hand side is P1 over density multiplied by G plus, remember density is the same as rho. When you see this is the same as density plus V1 squared over 2G plus Z1. This is H1. This is H1. This of the left hand side. This on the right hand side. H2 will be P2 over density V2 squared over 2G plus Z2. This is H2. You see the energy head. Call this the energy head. Energy head, all of the energy. This is the energy head. You see that H is not, there is difference between H and H. This is the big H. You will use this if you want to apply, or for instance this, you must multiply this when you are dealing with power. This H will use so much when you are dealing with the power. Right? So you must know your stuff there. You must know your stuff. Amen. Total head, that one. Remember the sum of all. This is H, total energy or total head. By total head. Must multiply all of that by total head. Isn't it? Total head. So it's important to have total head because power will be equal to W flow, the weight flow multiplied by this H. Depends, can be H1, can be H2. This is what will be power. Remember, we have this thing that says output must be equal to input minus, let's say, minus what? Friction power. Okay, let me just show this is what. Okay, let me just simplify this further. This, we know this. Remember, I've shown you this is the same as density multiplied by V, right? This will be density multiplied by flow, volumetric flow multiplied by H. This is power, is measured in watts. That must be power. That should be power, right? That should be power. Yeah. Must know how to calculate that power there. Right. Oh, gosh, that's cool. That is the power. 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 Can be power, the jet. What about now the force? Oh, force. What about the force? Remember, we can have to calculate the force. What about calculating the force? But I know that the force is equal to fluid mass multiplied by velocity. This is the force. But now we know that the fluid velocity, we've discussed about this. We said this must be equal to what? Must be equal to what? This is the same as what? mg multiplied by v. Oh, what time? Oh, okay. This, no. This is supposed not to be here. Remember, that is weight. Flow. Remember, this is mg, right? So this must be in seconds. This is the weight, but this must be mass flow, right? So yeah, this must be mass flow multiplied by g. That is the weight. Mass flow multiplied by what? What is mass? Mass is density multiplied by v, right? So gh. So the power here, simple, since I've derived that. See, the power can make it further, can be the power here, if it goes further, can be density volumetric flow multiplied by g gravity h. This is power, right? So the force, it's mass flow multiplied by v, velocity. Then this is the same as the p multiplied by v, right? This is the part v, the same as area multiplied by velocity, right? So when you substitute this there, we'll have density into area multiplied by velocity into v. When you apply maths, this when you multiply these two, we have area v squared. This therefore force will be p density multiplied by area v squared. So here our formula, these two, formula 1, formula 2, formula 1, formula 2, right? It's how we calculate this. You must know that these things here, this h is the h of the head of the total energy. So yeah, we have that. So so we had that. So I want us to check friction head. Just grasping this, just giving you intro. Friction head. Friction head. So we know that power is this. It's right, that is power. So power output must be equal to power input minus power loss. Take note, power loss is due to friction. Power loss will be W multiplied by friction head. You'll be given this friction head. This friction head will be given. If you're not given, friction head is equal to 4FLV squared over 2GD. This is the friction head. It's up to you if you are not given, you see, but this will be friction head, which is friction head is in mid is power loss. So power output, this is the power, but power input is W multiplied by H, the power input. So power output will be W H minus W HF. So this is, can take out the common vector here. We'll have H minus HF. That is an output power. And that is how we calculate an output power. So obviously efficiency, we know that efficiency is output over input multiplied by 100%. So multiplied by 100. So in other words, this will be output power. Whole of this, call it, the whole of this is what will be P out over P in, which P in is this, multiplied by 100. So this is equal to output power is W, here it's output power, into H minus HF, then this is W into H, right, flow, this and this cancel the same, this is H minus HFF over H multiplied by 100. This is efficiency. Actually here it's efficiency, just trying to simplify here. See, simple. H can be H1 or H2, depend on the question, what does it want. H1 is for jets. It's up to you, how will you apply this, right? Yeah, it's up to you. Remember, can be H at jet or H. Okay, let me say we are given a pipe like this. 0.1, you can say 0.2. You can find power at 0.2, 0.1, but this will be H2. This will be H1. Remember H. Remember the H. What is H? The H. Then let me do like this. Let me say, for argument's sake, you want to find power at H2. Power here at H2. Power at H2. Power at point 2 here. Let's say power at point 2 here. For that diameter, that must be equal to W, right, with the dot flow multiplied by H2, right? For argument's sake, we know this is equal to what? Is the same as P2 over density multiplied by gravity plus V2 squared over 2G plus Z2. You see? So this, all of this is the same as H2. For argument's sake, you want to find power here at point 1, here at diameter 1, we'll have W, right? Then this into H1. We know that H1 is the same as P1, density multiplied by gravity plus V12 over 2D plus Z1. This will be power. You just substitute the values there. Yeah, I'm fine. Hopefully this is good. For argument's sake, maybe here H, it will depend they want the friction loss where. But remember, if you have a pipe, when the friction loss will be here it start, it depends. Remember, substitute this for the argument's sake. Let me erase here. Let's say you want this output power. We know that the output power is this equation, right? That we've derived is this. And then I did this and I took out the common factor. Then I left with, start here so that we not forget. You know that power is this. So and then I said, then I took out the common factor minus H F, right? For the argument's sake, H, we don't know. Let me just say P G plus V squared over 2G plus Z, right? Brackets like this minus HF multiplied by W P out, right? This, what I'm trying to say, this is the total head. H is the total head or total energy using the Bernoulli's theorem. So you see, if you apply this, you'll be fine, guys. You just going to cruise nice. Thank you guys for your time. Do not forget to subscribe to my YouTube channel and stay notified whenever I post the new videos. Subscribe to my YouTube channel, click that notification button so that you'll be notified. Remember, I'm also doing N6 fluid mechanics. That means in next block you'll also need me. So just subscribe so that you'll be notified and click that notification button. And also send to your fellow classmate. Please just subscribe. Do not just watch. Support me so that I will bring some more videos. Thank you guys. Share and enjoy. This is long, right? I wanted to do some example, but this video is too long right now, so I think it is fine. Let me just end here. I will see you on the next coming session. when I'm dealing with other questions. Right, cool guys, sharp sharp.